Welcome to my lecture on transformations, this time with sound. So, a transformation is a relationship between random variables. And generally, the example would be anything such as y equals f of x. Okay, that's our transform. And the question is, what is the density function of y? Okay, and what's given, note, the density of x is given. So this generally works out in this way. We're going to use the density of x to obtain the unknown density of y. Okay, that's our general process. Okay, and we'll see lots of examples of y equals f of x with very concrete examples. But first, there's going to be some very useful facts that are useful to know. Okay. So here's facts. So the first is that the CDF of y, that's going to be the probability big Y is less than or equal to little y. And if this is a cumulative distribution, this is the integral of minus infinity to little y of g of y dy. And I'm going to call this capital G sub y. Then g prime of y is equal to g of y, the density function of y. So let me sum that up. So the derivative of the cumulative is the density function. And this is going to be critical. This is what we're going to use to solve these problems. Here's another fact. And this fact is called the fundamental theorem of calculus. Okay, and the fundamental theorem says this: if g sub y is this integral from minus infinity to y of g of y dy, then g prime of y is equal to g of y. Okay, and that is very, very similar to what we just used. In fact, the two are synonymous, but I'll use them in a very slightly different way. Okay. So I think it's time for a nice little example. So consider the transformation y equals 1 over x, okay, where x has an exponential 1 distribution, okay? And our goal is this. Determine the density of y. Here's what we're going to do. We're going to write down the cumulative distribution of y, and then take its derivative, which will give us its density function. Okay, so cumulative of y, I'm going to call that g of y. That is by definition the probability big Y, and I'm going to write this in a very specific way because it gets confusing which Y is which, is less than or equal to little y. My apologies while a helicopter goes overhead. Okay. Because I know the density function of y, I know it's exponential. Because I know that there's a relationship as random variables. In fact, if we go back, to this one right here, this is my transformation, y equals 1 over x. I can now use that. Okay, so I'm going to use 1 over x. I'm going to replace capital Y, which is my random variable, with x. Little y, which is in red, is the given value. That's the variable. So the cumulative y is g of y, and it's equal to 1 over x. Next, we'll solve for x. Okay, and this is going to be the probability 1 over y is less than or equal to big X. And then I'm going to take the complement rule. So 1 minus the probability big X is less than or equal to 1 over y. And because I know the density of X, so density of X is exponential, I can compute this probability as 0 to 1 over y of the exponential density. The exponential density is going to be e to the minus x dx. Okay, so I'll put that in here. And this is going to be 1 minus, now keep in mind there's a negative sign out in front, so it'll be minus e to the minus x, evaluated at 0, and 1 over y. Now, when you compute this, you're going to get 1 plus e to the minus 1 over y minus 1. So those cancel. Okay. So the cumulative of y is g sub y, and that's going to be e to the minus 1 over y. That's great. Okay, so I don't want the cumulative, I want the density. And the density is the derivative of the cumulative. That's g prime of y, which is the derivative of what's on top right there. So when I differentiate this, I'll have e to the minus 1 over y times the derivative of minus 1 over y. The derivative of minus 1 over y is going to be 1 over y squared. And that's our density function. But there's one thing that must be included. That is the interval for which this applies. And that interval is going to be the range of the transformation. Our transformation's 1 over y, and we have an exponential distribution for x, so x takes values between 0 and infinity. When x is 0, it limits, the range of y limits to infinity, and when x becomes very large, y limits to 0. So this is going to be, again, be for y between 0 and infinity. Okay. That is very important, and this right here, that's something that you'll be asked to determine. Okay, let's determine one more example of transformations. Okay. And this example is y equals x to the 4th power. Okay. Where x is normal 0, 1. Okay. And our goal is again to determine the density function of y. So we're going to proceed in exactly the same way. There will be one slight difference. Okay, so the cumulative of y is g of y, and that's the probability big Y is less than or equal to little y. But remember, big Y has a relationship as random variables to be x to the 4th is less than or equal to y. When we solve for x, just as we did before, that's going to be y minus the 4th root, let's write that a little more clearly, of y is less than or equal to x is less than or equal to the positive 4th root of y. Okay. And this is going to be this integral from minus, and let's write the 4th root like this. y to the 1/4 power to y to the positive 1/4 power of x, which is the exponential distribution, with mean 0 and variance 1. So 1 over root 2 pi times e to the minus x squared over 2 dx. Notice that this integral is symmetric and it's an even function. On a symmetric interval. So by calculus, this is going to be twice the integral from 0 to y to the 1/4 of 1 over root 2 pi times e to the minus x squared over 2 dx. Now, before I pick up with this calculation, notice in the last problem, we simply anti-differentiated this. But we didn't have e to the minus x squared. There is no antiderivative. So how can we figure out the density function? Well, we need to use something from calculus, and that's the fundamental theorem of calculus. Okay, and the fundamental theorem of calculus is going to say this. It says if h of y is this integral from 0 to y of this 1 over root 2 pi times e to the minus x squared over 2 dx, then h prime of y is exactly what's inside. Okay, and we're going to use this fact right here. Okay. So where we picked up last time was that g of y was twice this integral from 0 to y to the 1/4 power of 1 over root 2 pi times e to the minus x squared over 2 dx. Okay. Now notice here we have y to the 1/4 power. That's different than what we had in the previous slide. What we had in this slide right here is a single copy of y. But we can still use this very important fact called the fundamental theorem of calculus. Okay, and I'm going to use it in the following way. The only difference between these two is that instead of having y, I have y to the 1/4. So that's called function composition. Okay. Here we go. That is the cumulative. I'm not going to anti-differentiate it because I can't. Okay. So again, the density is the derivative of the cumulative. And this is 2 times h prime of y to the 1/4. And using the chain rule, this is going to be 1/4 times y to the minus 3/4. Okay, if only I knew the derivative of this thing, I'd be done. But wait, if I go back and I look at the fundamental theorem of calculus, I do. I know what the derivative is. The derivative is right here. So I'm going to use that fact. And this is the density function. And yes, we can clean that up with some algebra, but I'm going to leave that as it stands. Okay. Now, there's one last very important question. For what values does this apply? Well, if we consider the transformation, our transformation is y equals x to the fourth, where x takes on values between minus infinity to infinity. Those values come from the normal distribution. Implies the answer is, well, the smallest value that y can obtain is 0, and the largest is infinity when I raise x to the fourth power. So we're looking at this. Keep in mind the domain of x comes from its density. And this is simply the range. Okay. Well, that is my lecture, part 2 with, well, not part 2, but this time with sound. So I hope this helps. Thank you.